Almost ready, guys. All right. All right. So, good afternoon, everyone. My name, again, is Johnson, and I'm here to present my research here titled Massive Black Holes in a Radio. I'm working with Christina Nyland, who's my advisor, who's actually here today. Hello, Christina. Coming from NRL, and also Jenny Green. Here in the background, we have 6 optical images of some Atlas3D galaxies, which Christina Nyland did research on. And here we're looking at we're looking at these elliptical galaxies, and these galaxies are also red. And we want to look at more things. Why are these galaxies red? And I'll talk about that in the future. But before I get started, I would like to give some acknowledgements. One to my beautiful girlfriend, Jasmine Williams, because without her, I wouldn't be able to give this smooth talk to you guys today. Work copious time with her and also help me get through this program here at Princeton. Also, I'd like to thank my family as well for all the love and support they have given me. Also, my ancestors for being able to build this institution and allow me to come here to speak my truth here today. And also just the Princeton Post-Baccalaureate program just for helping me with the growth and everything that I experienced here in Princeton, New Jersey. So I appreciate everything. Thank you guys. So back to the talk. One of the questions that we really want to answer is what keep elliptical galaxies red? So here we have 2 optical images of the famous M87. Here we can see the whole galactic extent of M87 with a little bit of the jet coming out there as well. M87 is also an elliptical galaxy that is also red and dead. As we're saying, the stars are old, are very old, and it's called red and dead. I don't know where that comes from, but that's what we say. Here goes a zoomed out version of this galaxy that has a very extended radio jet, which we know is heating up the X-ray gas, which is keeping this galaxy red. So we want to know if this is true for all elliptical galaxies. Another question we want to ask is, does environment matter? Here I have 2 images. One, this image is to my right is NGC 1600, which lies in a poor group. This NGC 1600 is also known to be a red galaxy, which you guys can also see in this optical image. There was a zoomed in version here. And so we want to know, what is keeping this galaxy red in these poor groups. We know in large clusters like the Perseus cluster here, this is the X-ray image with the X-ray gas being shown here in the red. We know that radio emission, which can be seen here as the black because it's not detected in X-ray. Did it go back? Okay, sorry. Radio emission is on those black lobes. And so we know that the radio emission is being able to keep these clusters red. So we want to know if this happens for poor groups as well. So the survey that we use to answer these questions is the Atlas3D Survey, which was done by Christina Nyland, which is an integral field unit spectroscopic survey, which I will for now say IFU because I cannot say that spectroscopic word or spectroscopic. And so it also has a stellar mass cut at K less than negative 21.5. Also the volume limited, and it also has about 260 early time galaxies. And so what we can see in this plot here, on the x-axis we have stellar mass, on the y-axis we have velocity dispersion, and we can see how Atlas3D is complementary to massive, while massive is probably much more higher stellar mass. And so the survey that I worked on was massive survey, which with Jenny, is also IFU as well. We're probably the 100 most massive galaxy within 100 megaparsecs. And it's also got 120 early type galaxies. This is an example of IFU for NGC 1600. On the top, what we can see here is it has low velocity as the magnitude is probably like just an order of 10 magnitude for the velocity. But we also see some slow rotation happening in like the horizontal direction here. We also see a very high velocity dispersion in this galaxy as well. And we will denote what that means in the future. One of the telescopes that we used was the JBL. The telescope that we used to get this radio data was the Jansky Very Large Array. The data that I looked at was 1.5 gigahertz, which is the L band. It was able to get down to 4 arcseconds of resolution. Also, what was significant about the galaxy I was observing in L-band is 70 of the galaxies in L-band were already detected by the first survey, first NVS survey. And so what we were really doing is choosing these galaxies that weren't being able to detect any surveys, so we're trying to get a much deeper resolution or RMS noise. And so after getting all that data from the radio telescope, I took a copious amount of time doing this process called cleaning, or doing radio interferometry, which is a craft in itself outside of science. That being able to get this process, and so that was the bulk of the work that I took. A lot of painstaking time to get these blobby images that you are be able to obtain right now. And so with that, with using JBLA, we're able to get to RMS noise about 70 microjansky. At least all but 10% were detected out of all the massive galaxies, and we're able to get down to about like 10 kiloparsecs. Or 10 kiloparsecs was the average size of these radio blobs. So we were also trying to see about these radio blobs, like if they're extended, like the one in the middle, UGC 1332. And what I mean by extended is that the radio lobe is extends past the shape of the beam, which is in the bottom right corner. But most of them, we see galaxies like PGC 4776. You can look at, we see some more, just unresolved sources here. But we have, a special significant source right here, NGC 1573, which is a very special source. It's a double lobe source, which wasn't known to have a double lobe source before. So that's something that we can also go more in detail and look at in the future. But like I said, this is one out of the many, unresolved sources. Also in this slide, we see sources like NGC 2832 and NGC 7556 that looks like it may have, some secondary emission nearby in the detection. And so we also wanted to look and see if that's, if that's the radio emission coming from the galaxy, because maybe it could be something like NGC 1573, or maybe it may just be some foreground galaxy. So to kind of look more into that, we took the optical images, which shows us the extent of the galaxy, and overlaid it with the radio emission that we just saw here. So the red contours represent the radio emission, the black blobs represent the galaxy. And as we see in NGC 5073, the radio emission extends very far into the galaxy bulge, and can possibly, be one of the reasons that this galaxy is red. It's extended out to the bulge of the galaxy and heated up the X-ray gas. But galaxies like NGC 7556 is like it's within the envelope of the galaxy. So maybe there may be some other source leading to that. Also, as I said before, that may be a foreground galaxy. If you see in the optical image, there's also a little black blob there, and based off of the database that I found this on, this is radio emission coming from a foreground galaxy. Also, we have radio blobs like this, like PGC 4829, which is extended, but the galaxy it doesn't extremely extend that far out of the galaxy. And then in UGC 1332, we see that this the galactic bulge is kind of like horizontal, and this is kind of perpendicular to the emission is perpendicular to like the galactic bulge. So these are some of the interesting sources. Some other information that we're able to get from the radio data is being able to obtain a luminosity. Here we can see the 70 galaxies that were detected by FIRST, as I stated before, which has much higher luminosity than the galaxies that we probed, because as I said, we were trying to get some of those galaxies that were not detected in FIRST. But overall, comparing our massive luminosity with that of Atlas3D, we see overall we probe much higher luminosities than Atlas3D, which we wanted to do to complement that survey. So something else that I wanted to look at in my research was the ratio of the sizes. I wanted to see if most of the galaxies were like NGC 128, where the radio emission doesn't extend outside of the galaxy, or are they like NGC 1573, where it extends far beyond the galaxy. So I made a plot with that, with the x-axis being the optical size and the y-axis being the radio size, and that line being a 1-to-1 ratio where the radio equals the optical size. And as you see, there's only one galaxy, which is our friend NGC 1573, that only extends past the optical size of the galaxy. Everything else is below that. And so this may be, like, again, we can't necessarily conclude that the reason why these galaxies are red is from AGN feedback, at least not yet. But even though, you know, we have these blobby sources, there are some interesting signs or things that we can do. In science, we know two type of radio morphologies, which are denoted by FR1s and FR2. With FR1 being to my right, being a core-dominated source, core-dominated radio morphology, where the can't point to it, but the core is much brighter than the ends, than the jets. In FR2s, we have lobe-dominated, where it's like much brighter at the lobes than it is in the center. And we have a new class of galaxy or radio morphology, which is denoted by Baldy, called FR0s. And those are similar to FR1s, where it's core dominated, but it doesn't have the jets. And so they're also they're compact sources with around a few kiloparsecs, which I denoted before. Most of them, the average size is about 2 kiloparsecs. And so these are new class that also study that we can also look at with our research. Something that our advisor Christina did in her paper was being able to look at the star formation rate or see where the luminosity is coming from in the galaxies. So this is applied with H2, which is a tracer for star formation. Say it right. Tracer for star formation with radial luminosity on the y-axis, and this line here represents the line where luminosity is proportional to star formation. And this is a 5 sigma line where everything that falls in between here is, you know, a probability that it is formed by star formation. And as you see, for most of her galaxies, they all fall within the star forming region here, with a few of them falling outside of the star forming region. So we did that same little trick with our galaxies as well. You know, the same thing on x-axis being H2 and the y-axis being luminosity. Again, the green line now denote the 5 sigma line for star formation. And, you know, we have, like, you know, kind of 50-50 within, but based off of the upper limits on the H2, we can't really conclude that this is being done by star formation. We actually believe, since it's much higher stellar mass and much bigger black holes, that this is all coming from the radio emission is coming from the AGN. And like I said, we can see that based off of the high error bars within the x-axis. And so something else that we wanted to, or something else that we looked at that also was observed in Christina's paper was radio detection fraction rate relative to the stellar mass. On the x-axis stellar mass, y-axis is radio detection fraction rate. And what we see is as we get higher in stellar mass, we get a higher detection rate. How we can better see that is in this plot here, which has M star with stellar mass on the bottom and radial luminosity on the y-axis. We see the blue dots represent Atlas3D galaxies and the red dots represent massive. And we also, you know, see as we get higher stellar mass, we also get higher luminosity as well, which can denote why we're getting a higher detection fraction here, because it's, you know, much easier to see much more luminous objects. And so, even though we see, you know, there's a high correlation with stellar mass and luminosity, we wanted to also check in our research if there's other parameters that may correlate with luminosity. So one of the first parameters that we looked at was environment, which is delta, which represents the overdensity on a 5 megaparsec scale. And when we looked at delta versus luminosity in 3 different mass bins. Stellar mass bins, and we also ran a Kendall Tau test on these things to see if there's any correlation. And based off the results, there is no correlation. In this, the p-values are not significant. In these 2 cases here, the p-value is significant, but still the correlation value is not significant enough to be able to get any correlation or any results. So it looks like the answer, it doesn't really depend on environment. Based off of the data points that we have here. The next point of thing that we also wanted to look at, that was looked at in Atlas3D Survey, was this parameter velocity over velocity dispersion. And so on this plot here, this will also be, this is like a Hubble tuning fork. We have the x-axis, which also can be denoted as velocity over velocity dispersion. For the slow rotators, velocity is much lower than velocity dispersion, and for the fast rotators, the velocity is much higher than the velocity dispersion. And so what we see in Christina's paper, or the Atlas3D galaxies, is the circles represents the fast rotators, while the triangles represents the slow rotators. And we see that there's a lot of fast rotators in our sample. What we're trying to do in massive is look at more slow rotators. And so looking at that graph for my plot, we have, on the x-axis velocity over velocity dispersion, also the rate of luminosity, and we see that most of our galaxies, which massive is denoted by blue, is in this rate regime, slow rotators. So we also wanted to look at this and see if there's any correlation with any correlation with V over sigma with luminosity at different stellar mass. The same trick that we did with the environment. And so, looking at this again, we still don't have results that are any correlations or anything like that. Again, this is a significant p-value, but the correlation value is not high enough for any significance. And so we weren't able to conclude that there's any correlation with lambda as well, or this V over sigma parameter. So, yeah. And so, in summary, we still have some work to do, and we still have some work to do, and be able to need to look at more things, look at more look at more things to be able to get more information on the data that we obtain. But before going any forward, I think we need to stop for a little bit, and let's rewind, go back in time a little bit. Let's stop and think, and let's really start to think, like, how do we get to these myriad of questions? You know what I'm saying? Like, it all started with like one question that we asked. What are we? Who are we? Where are we at? You know what I'm saying? And from that process, it can develop something like the scientific method. The apple fell on Isaac Newton's head. He asked the question, why did this apple fall? Then he came up with what we know today as classical mechanics. And we did that through a scientific approach. But also in science, we see that the more questions that we answer, the more questions that show up. Something like a fractal representation. The more questions that keep getting answered, it keeps going to infinity. And so what I would like to offer, Jenny also said this as well, is I got my iron in a lot of fires, is I would like to offer a new approach, ideological approach, a supplemental approach to that which we call science. And this supplemental approach that I call is called SankofaMaat. Which is made of two words, Sankofa coming from Ghana, Maat coming from Kemet, which means Sankofa means go back and get it, and Maat means truth. So I'll put these two words together to go back and get the truth. And this derives from the 7 Kemetic laws of Egypt, or Kemet, and also the 42 ideals of Maat. I also have handouts, worksheets, if you guys want to see any of that, or if I can pass them out or anything like that. And so just to explain a little bit more on that, the 42 ideals of Ma'at is like an extended version of the 10 Commandments. Why this is important, or why I'm putting this into the ideological approach called SankofaMaat, is because doing the 42 ideas of Maat help us be able to collaborate and be cohesive with each other, be able to work together peacefully, and not more and less of a competitive environment, and more of a completion and collaborative environment. And so this, like I said, I have a handle on this. I'm not going to go through all the laws, but mainly just saying I will be a good person, and I'll be a good person to all those people around me. Another one of the things that it's based off of is the 7 Hermetic laws, and these are like some universal laws that we can see constantly in all the science that we do. And so, for example, the first one is the principle of mentalism. I think Descartes got at that a little bit when he said, I think, therefore I am. He made that statement saying that all things come from the mind. All these things, like this presentation that I presented here today, came from my mind. The chairs is made, everything came from a thought. and then manifest it into this thing that we call the physical reality. The principle of correspondence, as above, so below, as above. The principle of vibration, the principle of polarity, the principle of gender, there's the principle of rhythm, and there's also the principle of cause and effect. Like I said, I have a worksheet, so I won't go through all of them, but the ones that I would like to highlight is, let's look at the principle of vibration and rhythm, something that we observe a lot in science. If it wasn't for the vibration of an atom or the particles, it wouldn't be able to create these electromagnetic waves that we can detect here on Earth, which create these spectrums that we observe, which is something like a rhythmic pattern. So we see these things happen all the time. We also know, an object at rest stays at rest, and an object in motion always stays in motion. So these atoms that are vibrating at a very small level always vibrate, unless it would equate to absolute zero, which we know is theoretically impossible. Another law that shows up in science a lot is cause and effect. Right? I think Isaac Newton also got at this as well, or he had knowledge of this as well, when he made the statement, for every action there is an equal and opposite reaction. It's just this thing that there's a cause and effect to everything that happens in this reality. And another law that I would like to talk about that I can see directly applying to my project is the law of correspondence. And hopefully, if we have sound, I can let Bart Simpson tell us something about this. Oh no, we don't got sound. You guys know, anybody else got sound? What do you say?
Make sure it's okay on there.
Okay,
You have the HDMI?
I have the HDMI,
Yeah. It's muted. It's not muted on your laptop?
No, I don't think so, but I can also...
Okay, hang on. Make sure the sound is on here. Ah, there's the thing. Okay, try it again.
Zoom?
Did it work?
No, I think I'm going to try this. I'm going to put this other
Something just happened.
connection, and I think I'll just play it off my laptop. Let's see if that works.
Or you can play it for everybody afterwards.
Yeah. Is this showing up?
We're also getting close to that half-hour mark, so.
No problem. I'm almost finished.
Yeah.
Man. All right. Well, I'll just talk you guys through it. No, it's not gonna go. But you guys can just watch the thing. So that may have some epic music happening right now. Zooming out. Still some epic music. Might have some sound effects. See the Earth orbit. Yeah. You see our friends. We're looking for them, man. We're looking for them. Galaxies. Oh, what? What is this? What? Okay, yeah. And then it goes to deep. Okay. Is that the cosmic web? Yeah. Zoom back to that. And so there he made a funny comment that said, wow. And so that's like an example of the, at least what I see as an example of the law of correspondence. A law of correspondence. And I can show further how I apply that to the project. And so again, like I said, I think SankofaMaat, or the ideology of SankofaMaat is complementary to science. And the reason why it's complementary to science is because I think science studies the physical realm and the physical phenomenon very well. But with SankofaMaat, I think it helps us understand, or it incorporates the mental realm and the spiritual realm. Just like the mental realm are thoughts. Like right now, everybody's thinking, I can't read you guys' thoughts or see your guys' thoughts, but I know that all you guys are all thinking right now. And it's something similar to galaxies that have this matter and that's surrounded by dark matter. This thing that we don't understand and really can't interact with. Maybe the mental realm. Also, we have like I said, incorporate the spiritual realm, something else that we may not understand even more, which is something called dark energy. Something that we still can't figure out how to interact with and stuff like that. And so I believe that maybe incorporating methods like SankofaMaat will probably be able to get more understanding of the reality that we live in today. And also on top of that, it also takes the knowledge and information that we learn and also help us apply it to our life on a day-to-day basis. and help us incorporate it on a more practical sense as well. So that was also one of the goals of SankofaMaat. Again, I have a handout for this as well. And so applying the law of correspondence to my research, this would have been the original topic if I was presenting this through the SankofaMaat method as well. So it would be, massive black holes, right? Holes as a group of collective of people. If you guys had my talk that I did over there before, just talking about this on the radio frequency, observing the radio, frequencies. These are black holes that exist, in all countries around the world, which we may not see all the time in science and stuff like that as well. But we still can get a lot of information from their culture, through dance and stuff like that. They also have their own methods of studying. And then speaking of dance, we had one of your own students, David, showed how science can also be explained through dance and stuff like that as well. And so, just saying that's one thing. And so just to go on to future work, talking about some of the things that I'm going to be doing in the future is I'm currently working on developing this ideology even more. I'm working on creating this as a program and trying to offer it to students. I'm calling it a STEAM program, which is incorporating science, technology, engineering, art, and mathematics. And trying to incorporate this in a way that's not traditional and helping us be able to apply the methods that I said before. And so, thank you guys for allowing me to give this presentation and listening to what I have to say today. I appreciate you guys' time.
Any questions for Liz?
I wonder if I can ask about the Kemet, which you made reference to.
Yes,
what is the history there? It's a term that I'm not familiar with.
So the name Kemet, as I know, all things in the world was renamed and stuff like that, based off of colonization and different things like that. The name Kemet comes from Kim, which is it means like black or dark. You know what I'm saying? And the name Kemet was like the land of the dark. And so we also can see this in alchemy, right? The study of this, or chemistry, right? The study of these words, Kim. Kim is its roots all the way back then. So that was one of the original names that the people from Egypt called their plane. Yes, and you can also see that on the walls of the Egyptian walls and stuff like that, and also from the gods and stuff like that. Thank you for that question. Appreciate it. Oh yeah, I also want to say I don't know if if anybody's also interested in that the method and technique, and also maybe have funding or know any institutes or place where I can do this type of research. I'm all ears and willing to listen to the opportunities that are out there.
Coming back to the first part of your talk, in those cases where you can resolve the radio emission, so you know the size, have you tried to compare the minimum pressure in those lobes to the pressure of the galaxies surrounding it?
What do you mean by pressure?
Well, there's a standard way of estimating the minimum energy of a synchrotron emitting.
Well, remember when you showed Perseus how the radio was where the X-ray isn't?
Mm-hmm.
So Jeremy's asking about the balance between the plasma that's in the radio and the pressure from the X-ray gas. Basically,
exactly.
How much energy is the radio emission putting back into that gas?
Okay, and so I think that would have to be in terms of getting future work and be able to compare the radio with the X-ray, or can we do that with the data that we have?
Well, we could do the echo-partition estimates and pressure estimates down the line. It's just something we haven't done yet. For Atlas3D, we've done that a little bit in the 2017 paper. But yeah, that's to be done.
And Andy's got more than half of the massive stage will have X-ray by now. So we actually will have
everything else.
That's going to be a follow-up. Do you see any evidence for X-ray shadows as you showed in person?
We don't even, well, yeah. All right, let's thank Louis again, and appreciate